This is number 3 from the table of values FRQ practice problems. Twice differentiable function. So again, this means it's a smooth curve, at least a polynomial of degree 2. F and g are defined for all real numbers. Value of f, f prime, g, and g prime for various values are given in the table. Part A, find the x-coordinate of each relative minimum. So if we're talking about relative minimum for f and we're looking at an f, if we're looking at an f prime graph, then critical point is where f prime changes signs from negative to positive. So wherever f prime changes from negative to positive, okay, and where there's a slope 0 that exists in between, then we know that there must be a relative minimum. Okay, and here, even though that's a critical point with a slope of 0, a negative slope followed by a negative slope is not going to result in a relative minimum. So only relative minimum at x equals 1, because f prime changes signs from a negative slope to a positive slope. Part B, explain why there must be a value between -1 and 1 such that f double prime of c is equal to 0. So f double prime, we're trying to guarantee a specific derivative value, and we can extend Rolle's theorem to find f double prime to guarantee, determine whether we can guarantee where f double prime is equal to 0. So with mean value theorem or Rolle's theorem, we can say that since f of x is continuous and differentiable and our endpoints produce the same y value, we know f prime of c is equal to 0. And we can also apply that from first derivative to the second derivative. Since f prime is continuous and differentiable, and f prime of 1 is equal to f prime of -1, which they're both 0, then we can guarantee that there must be a place where there's a slope such that f double prime of c is equal to 0. So we're applying mean value theorem. We can also call it Rolle's in this case because we're trying to guarantee a slope 0. And normally it's for f and f prime, but we can also bring it one level down, one derivative down, start with f prime, and guarantee an f double prime of a value equal to 0. Right, for part C, we have h defined as natural log of f of x. Find h prime of 3. So if I want to find h prime of 3, I have to find the derivative. To find the derivative, this is a function within a function. So the rule is natural log of u is u prime over u. So natural log of f of x is going to be f prime over f. So now we can replace each x with 3. We get f prime of 3 over f of 3. We look at our table. F prime of 3 is going to be f prime of 3 is going to be at 1/2, and then f of 3 is going to be at 7. So f prime of 3 is 1/2, f of 3 is going to be 7. So we have 1/2 over 7, which reduces to be 1/2 times 1/7, which is 1/14. Okay, for part D, we're trying to find the antiderivative, or trying to evaluate this this definite integral. But notice that with all this mess, we have to think of this as a u substitution problem. But now the u value is going to have to involve function notation. So we'll let the u value be what's inside the bracket here. So we'll let the u value be g of x. And with u substitution, we always find the derivative once we find the u value. So u prime or du dx is equal to g prime, right? G becomes g prime. We solve for dx, we get du over g prime, and then we make our substitutions. We're going to replace our g of x, and we're going to replace our dx, and see if our g prime will cancel out nicely for us. Get everything in terms of u. So we get f prime of u times g prime times, and then dx gets replaced with du over g prime. G prime cancels out, and then we're left with integral of f prime of u. And we know that we have a rule for f prime of u, which will just bring it up to f of u. And with f of u, we want to evaluate the bounds, but we have to be careful because we don't want to use the negative 2 and 3 in this form, because this is in terms of x and this is in terms of u. So let's bring our antiderivative back in terms of x. So replace u back in terms of x. So u back in terms of g of x. So now we can plug in our upper and lower bounds. Upper bound 3 gets plugged in for x. We get f of g of 3 minus, then plug in the lower bound, f of g of negative 2. So now we go to our table of values. G of 3 is going to be 1. And then g of negative 2 is going to be at negative 1. So we replace g of 3 with 1, g of negative 2 with negative 1. But it's still stuck in function notation, so we go through one more round of evaluating. F of 1, we go to our table of values. F of 1 is equal to 2, and then f of negative 1 is equal to 8, and so 2 minus 8 is equal to negative 6.